What's going on, guys? In this video we're going to be covering the dreaded principal component analysis. So I'm hoping to jam pack it all into this one video, but we'll see. So what is principal component analysis? So principal component analysis is an unsupervised learning algorithm, and thus far we've discussed k-means and hierarchical clustering, which were two unsupervised learning algorithms, but they were clustering algorithms. Principal component analysis is a dimension reduction technique. So what this means is going to create a new set of features with the goal of maximizing the variance or information in the first few newly created features called principal components. So these newly created variables or principal components are found using linear combinations of the original variables. And the maximum number of principal components we can create is going to be the minimum of either our n-1, where n is the number of observations, or m, which is the number of variables. So the reasons for why you want to use principal component analysis is to identify hidden patterns, reduce dimensionality in your data, and to highlight the correlations that exist in your data. So now we're going to go over all the terminology that's going to pop up as we cover principal component analysis. And then in the next section, we're going to learn how to solve all these sections by hand. So the first step when performing principal component analysis is to standardize your data. So if your data is not on the same scale, you will get different results. So after you standardize your data, you can run your principal component analysis algorithm. And what this will create is a set of load-ins. So for each principal component, you're going to end up with the number of load-ins as you had original variables. So since our data set had two variables, we're going to end up with two load-ins per principal component. So on the left is just going to be the annotation you would use to represent your load-ins. And on the right is the actual values you would get if you were to run principal component analysis using the data above. So we're not expected to solve for these load-ins by hand, but there's two tricks we're going to learn later on, where say if you're given this value and this value, you could solve for the other values. So these load-ins are chosen to create a line that follows the original observations as close as possible, and to create a line along which the data varies the most. So these 2 points seem counterintuitive, but I'm going to try to prove now why they're not. So in the plot, we have our original scaled data. So if we were to add our 0.707 and 0.707 for principal component 1, that point would fall right about here. So we can connect this point through our origin. Because our data was scaled, the mean of our data is going to be 0 for both variables. So this line would represent our principal component 1, or PC1. Now, it's easy to see how this line would create a line that follows the original observations as close as possible. But how do we prove point 2? That we create a line along which the data varies the most. So if we were to copy this, and then we rotate it so that our principal component 1 line is along the x-axis, and then we add our points to our line, then we can see that the line we created also caused our observations to be as far away from each other as possible than if we were to create any other line. So this is another way of saying that we create a line along which the data varies the most, or we created the highest variance we can among our observations by choosing this line. Now for principal component 2, if we were to plot that, we can see it's at 0.707 and negative 0.707 for x2. So if we were to add that to our plot, 0.707, negative 0.707 would fall right about here. And again, we're going to extend this through the origin because our data is centered to have a mean of 0. And notice that the principal component 2 is perpendicular to our first principal component. Or the word that we're going to use when we're using principal components is the lines are orthogonal to each other. So what this means is that the correlation between principal component 2 and principal component 1 is going to be 0. And then any other principal components we add, the correlation between them all is also going to be 0. So the next principal component we add we want to capture as much variation we can as possible, with the restriction that the correlation with all previous principal components is 0. Scores. So we just covered load-ins, and we learned that for each principal component, we're going to have one load-in per the number of variables for a principal component. So we learned that our data had 2 variables, so it's going to have 2 load-ins per principal component. So with scores, we're going to have as many scores as there is observations for a principal component. So since our data had 8 observations, for each principal component, we're going to have 8 scores. So we're going to learn later on that we can solve for these algebraically by using our load-ins and create linear combinations of our load-ins. We will be able to calculate our scores. Then after we calculate both our load-ins and our scores, we're going to be able to combine the results from both of them onto one plot, and we're going to be able to make a whole bunch of different interpretations from this plot, called a biplot. And another thing we can do with our scores is we can come up with the variance explained, or the eigenvalue for each of our principal components. And from this, we can find the proportion of variance explained for each of our principal components. And using this information, we can add it to a Scree plot, where ultimately we're going to have the number of observations on the x-axis and the variance explained, or the proportion of variance explained, on the y-axis, and this will give us an indication of the number of principal components we can use in our final data set. So now we're going to start solving for the different parts of principal component analysis by hand. So first off, we have the load-ins, which I said you didn't necessarily have to learn how to solve for by hand, but there's 2 rules you have to know, where if you're given a certain set of load-ins, you can solve for the other set. So the first rule is going to be that the sum of squared load-ins for each principal component must equal 1. Or the summation from j is equal to 1 to p of the squared values of our load-ins must equal 1. So that means if we were to sum up the square values of these values, we should get 1. If we were to sum the square values of these values, we should get 1. And the same for principal component 3. So we can test for that now on our data set on the right, or our load-ins on the right. So if for principal component 1, if we were to sum up our squared load-ins, so that would be 0.68 squared plus 0.68 squared plus negative 0.28 squared, we should get 1. And if you plug that in a calculator, you will. Now for principal component 2, again, if we sum up our squared values for our load-ins, are negative 0.17 squared plus negative 0.22 squared plus negative 0.96 squared, you should get 1, which if you plug it in, again, you will. And then finally, for principal component 3, we did 0.71 squared plus negative 0.7 squared plus 0.04 squared, you will again get 1. So you can imagine how on the exam they would try to ask this question where they'd leave some blank and you'd want to sum it up and just solve it algebraically. Now for rule 2, which stems from the fact that the correlation between your principal components should be 0. So if you sum up from j is equal to 1 to p of your load-ins for your first principal component times the load-ins for your second principal component, you should get a value of 0. So the way to test that is if we were to multiply this load-in by this load-in, and then add it to this load-in times this load-in, and then add it to this load-in times this load-in, we should get a value of 0. And then the same thing for between principal component 2 and principal component 3. If we multiply this one times this one, this one times this one, this one times this one, add them up, we should get 0. I mean the same thing for principal component 1 and principal component 3. So now we're going to solve for that by hand. So on the right, we see that if we're to multiply 0.68 times 0.17 plus 0.68 times negative 0.22 plus negative 0.28 plus times negative 0.96, we should get 0. So we can test for that. So 0.68 times negative 0.17 plus 0.68 times negative 0.22 plus negative 0.28 times negative 0.96. And if you plug this into your calculator, you will get 0, minus rounded. So that's between principal component 1 and principal component 2 have a correlation of 0. And then we can do the same thing for principal component 1 and principal component 3. So we would just do 0.68 times 0.71 plus 0.68 times negative 0.7, and then plus negative 0.28 times 0.04. And you should get about 0. And then you can do the same thing for principal component 2 and principal component 3, and again you should get a value of 0. So we just covered load-ins, and now we're going to cover scores. So scores you are expected to solve for by hand, assuming that you're given the load-ins already. So the formula that we're going to use is that a score is going to be equal to the summation from j is equal to 1 to p, and then times our load-in value times our original observation. So if we want to find the score for observation 1, principal component 1, the values that we're going to use are principal component 1 values, and since we're using observation 1, we're going to be using observation 1 values. And now we're just going to find a linear combination of these values. So to do that, we would just multiply the values together and add them up. So it would be 0.68, and then times our observation 1 for x1, which is 1.16, plus 0.68, and then times our x2 value for observation 1, or 0.85, and then finally negative 0.28, and then times our x3 value for observation 1, which is just 0. And this will produce a value of 1.36. So our score for observation 1 of principal component 1 is just going to be 1.36. So now we can solve for observation 1 principal component 2, or this value right here. So the values we're going to use to solve for this, so observation 1 principal component 2. So we're going to use principal component 2 values, and again we're going to use observation 1 values. So we're going to take the linear combination again, so it's going to be negative 0.17 and then times 1.16 plus negative 0.22 times 0.85 plus negative 0.96 times 0. And this will produce a value of negative 0.39. And then if we want to find observation 1 principal component 3 value, we would be using these 3 values for principal component 3, and again we're using the observation 1 values. So 0.71 times 1.16 plus negative 0.7 times 0.85 plus 0.04 times 0. And this will produce a value of 0.23. So we add that to our chart. And now we can do one more example where we're going to use observation 2, principal component 1. This value right here. So the values we're going to use, observation 2, principal component 1. So principal component 1 values, these 3 values. But now we're going to dip into observation 2 values instead of observation 1. So 0.68 times 0.19 plus 0.68 times negative 1.08 plus negative 0.28 times 0. And this will produce a value of negative 0.6. So I filled in the rest of the values if you want to try them yourself if you're still not getting the pattern. Variance explained. So each principal component explains as much of the variation as it possibly can. So this means principal component 1 is ultimately going to explain more variance than principal component 2, and principal component 2 is going to explain more variance than principal component 3, and then so on, so on, so on. So the formula that we can use to calculate the variance explained from each of our principal components is just going to be equal to the sample variance, but we're going to be using our scores. So these are the scores that we just calculated in the last example. So the formula that we're going to use to calculate the variance of our principal components is just going to be the summation from I is equal to 1 to n, where n is just going to be the number of scores per principal component, and then times our score minus 0 squared over n minus 1. So notice that we're using minus 0 instead of minus the mean. So the reason for this is that the mean for all our principal component scores is going to be equal to 0 because we centered our data. So if we were to sum up these values, so 1.36, negative 0.6, negative 3.4, negative 1.72, 1.3, and then divided by 5, we would get a value of 0. And then the same thing for principal component 2, principal component 3. So when we're finding the variance of our principal components, we can just ignore this minus 0 fact, and this is just going to become the summation from I is equal to 1 to n of our scores squared, and then divided by n minus 1. So if we want to calculate the variance of our principal component 1, we would just do 1.36 squared plus negative 0.6 squared plus negative 0.34 squared plus negative 1.72 squared plus 1.3 squared. And divided by n minus 1, which is just 5 minus 1. And this will produce a value of 6.97 over 4, which is equal to 1.74. So the variance of our first principal component is 1.74. So now we do the same thing for our second principal component. So we're going to sum up the square values, so negative 0.39 squared plus 0.21 squared plus 1.56 squared plus negative 0.98 squared, and then finally negative 0.39 squared, and this will produce a value of 0.937. And then finally for principal component 3, we can do 0.23 squared plus 0.9 squared plus negative 0.38 squared plus negative 0.35 squared, and finally negative 0.39 squared. And this will produce a value of 0.32. So these are going to be the values of the variance of our principal components, aka our eigenvalues. So now that we found the variance explained by each individual principal component, we can find the proportion of variance explained for each of these principal components compared to the other principal components. So for principal component 1, the proportion of variance explained is just going to be equal to the variance explained by our first principal component, and then over the variance explained by all our principal components. So it would just be 1.74 plus 0.937 plus 0.32. And this will give a value of 0.58. So we can say, of the total variation in the dataset, principal component 1 explained 58% of it. Now for principal component 2, the proportion of variance explained will again be the same formula, but now we're going to have 0.937 in the numerator. And then the denominator will stay the same. And we get a proportion explained of 0.31. And then finally, for principal component 3, we just do 0.32 divided by 1.74 plus 0.937 plus 0.32. and we get a value of 0.11. So since our data only had 3 variables, the maximum number of principal components we can have is 3. So all these principal components together should explain 100% of the variability in the data. So if we add up our 0.58 plus 0.31 plus 0.11, we'll get a value of 1. So we successfully covered 100% of the variability in the data using all the possible principal components. Now, another thing to notice, if you look at the denominator, 1.74 plus 0.937 plus 0.32. So ignoring rounded, we would get a value of 3 for this. Now, since our data only had 3 variables, and we standardized each of our variables, the variance for each variable will be 1. So when we sum up the 3 variables with variance 1, the total variance in our data is 3. So that's why our denominator would be 3 if we standardize our data. So using now our proportion of variance explained, we can add it to our plot, which is called our Scree Plot. So the first principal component explained about 58% of the variability. Our second principal component only explained about 0.31 of the variability, and then our third principal component only 0.11. So just to make it clear how you'd make an assumption from our Scree plot, on the right we're going to have an example with more than 3 variables. So let's say that the proportion of variance explained by our first variable was right about here, second here, third here, and then there was a big drop. So this is what our proportion of variance explained, or Scree plot, looked like if we were to have 8 principal components. Then it's easier to see that if you were to stop at only 3 principal components, you can capture a large proportion of your data. Where once you start getting past 3, each principal component is only going to explain a small proportion of the variability. And then as we move across, each principal component is going to explain less and less variability. So this is just from the construct of how principal components work. So now that we already calculated for our loadings and scores, we can add them to our Biplot. So first we're only going to be concerned with our loadings. So here on the right we have a plot that ultimately is 4 axes. We're going to have our x1, x2, and our y1, y2. So x1 and x2 are going to be concerned with principal component 1, while our y1 and y2 are going to be concerned with principal component 2. So notice that principal component 3 isn't included in this graph, so we can just ignore this for now. So now if we wanted to plot our loadings, we essentially have 3 groups of observations. We have 0.68, negative 0.17 for variable x1. We have 0.68, negative 0.22 for variable x2, and we have negative 0.28, negative 0.96 for x3. So if we wanted to add our x1 to the graph, it's going to be at 0.68 for principal component 1. So since principal component 1 is concerned with how far left or right, that observation would fall right about here for our x-axis or x2 axis. And for our y2 axis, it would fall at negative 0.17, so right about here. So where these two lines intersect, or where our x1 value would fall, will be right about here. Now for our x2 value, it's again going to be at 0.68 for our x2 axis, and for our y2 axis, it's going to fall at negative 0.22. So it's going to fall slightly beneath our x1. And then for x3 variable, it's going to fall at negative 0.28 for our x2 axis, and negative 0.96 for our y2 axis, which is going to be way down here. So this will be our x3 variable. So now that we plotted our loadings, we can plot our scores. So I just copy paste this. So for our load-ins, we are concerned with our x2 and y2 axis. For our scores, we're going to be concerned with our x1 and y1 axis. So the x-axes are still going to control our principal component 1, and our y-axes are still going to control our principal component 2. Again, we're not worried about principal component 3. So let's say our x1 was in a range from -2 to 2, and we can do -2 to 2 again for our y1. So if we want to plot our first score, we're now going to have 5 group-ins. We're going to have 1.36 and -0.39, -0.6 and 0.21, -0.34, 1.56, -1.72 and -0.98, and 1.3 and -0.39. So now we're mainly focused on our x1 and y1 axes. So for our first score, it's going to be at 1.36 for observation 1, which would fall around here, and then it's going to go up to -0.39. So it would fall right about here. So that's going to be our score 1. Now for our score 2, it's going to fall at -0.6, so principal component 1, so we're concerned with our x1 axis, and it's going to go up to 0.21, so right about here. For observation 3, -0.34, 1.56, that's going to be way up here. Observation 4, -1.72, -0.98, so right about here. And finally, observation 5, 1.3, -0.39, which will fall around this mess right here. So here we created our basic biplot using our original data to create our scores in our load-ins. So this is a biplot I made in R that we're going to use to learn how to interpret these plots. So first off, notice that the load-ins are on the bottom and the left instead of the top and right. So the way you'd be able to tell this is that if you look at the intervals, the interval goes to less than 1. Meanwhile, on the top, they go to greater than 1. So since the sum of squared load-ins we learned must equal 1, then this means each individual load-in value has to be less than 1. So that's how you would be able to tell which one's the scores and which one's the load-ins. So here we have the top and the right are scores, the bottom and the left are the load-ins. Now first, let's try to interpret our load-ins. So we're going to have 4 variables: swimming, sprints, and hurdles, and javelin. So notice that the farthest values to the left or right are hurdles, sprints, and swimming. So this is another way of saying, since principal component analysis is our x-axis, that whichever values are the most left or right have the biggest impact on principal component 1. So we can say that hurdles, sprints, and swimming are the biggest factors in determining our principal component 1. Now for principal component 2, which is the y-axis, whichever values have the furthest or highest on the y-axis or lowest on the y-axis have the highest impact on principal component 2. So we can see that javelin has a strong impact on principal component 2. Now if you notice, hurdles and sprints are very close together on our biplot. So this is another way of saying that these two variables are highly correlated with each other. And then if we look at swimming, it's on the exact opposite side of our principal component 1. So we can say that swimming is negatively correlated with hurdles and sprints. And then javelin is uncorrelated with either our hurdles, sprints, or swimming, because it doesn't follow forward to the right or to the left. And now we can examine our scores. So for our scores, we want to see where they fall with respect to our principal components, just like we did for our load-ins. So if you notice, Jason, Fred, Liam, and Scooby all fall very far to the left of our first principal component. So we can say that these 4 people are good at hurdles and sprints, but they're bad at swimming. Meanwhile, on the right side of our plot, our high values for principal component 1, we can see that Corey and Paul are very good at swimming, but they're bad at hurdles and sprints. And then if we want to look at for our principal component 2, we would look for highest values and lowest values. So now we're concerned with javelin. So we can see that Edward is very good at the javelin. And Drew and Flynn, who are on the opposite side of our plot, or small values for our y-axis, are bad at the javelin. So by using a biplot, we're able to find both correlations and group our observations to see which load-ins they fall closest to. And these names, you can just think of this as like observation 1, observation 2. It's just naming the observations. Now on the right, we're going to have another biplot, and it's going to depict the exact same thing. So the reason for this is that there's one random element that is created when we create our principal component analysis. And that's essentially whether you're... Now on the right, we have the exact same biplot, except it's translated across the x and y axis. So the reason for this is that when we initially create our load-ins in principal component analysis, they are unique, meaning if we did the exact same things, we would get the exact same values, except they're unique up to this sign. So for instance, for our first load-ins, let's say we got 0.71, 0.71, negative 0.71, and 0.71. So this is the exact same as saying negative 0.71, negative 0.71, 0.71, negative 0.71. So the random component when you first run your principal component algorithm is if you multiply all values by -1, you'll get the exact same results. So if you were to run the same algorithm, you would just as likely get this as you would likely get this for your load-ins. It's just based off a randomness element. And then after you go through, you use your load-ins, and you come up with your scores, all the scores would be the exact same values. Again, they would just be multiplied by -1. But looking at our biplot, we can arrive at the exact same conclusions. So again, we can say that sprints and hurdles are highly correlated. Swimming's negatively correlated with sprints and hurdles. We can see that javelin's not correlated with the other 3. And Edward is really good at javelin, just like we learned on the left. Drew's really bad at javelin with Flynn. The best swimmers, or we can say the best sprinters, are Liam. So we arrive at the exact same conclusions and the exact same results, just everything would be multiplied by -1. So that's what we mean by unique with principal component analysis. Unique up to the sign. So we covered principal component analysis, now we're going to cover principal component regression. So the way principal component regression works is you're going to include the results or the scores from your principal component analysis as your inputs instead of the original observations. And the pros of doing this is that ultimately you're going to be able to control the complexity of your linear regression model. So you can control the complexity by when you add more principal components, your bias will decrease, but your variance will increase. So one way to control the variance of your model is just to include less principal components. Now, the way you choose the number of principal components you want to include is you would just use cross-validation and treat it just like you would a tuning parameter. So you would try different numbers of principal components, so say either principal component 1 and principal component 2, or principal component 1, principal component 2, and principal component 3. So you would just use cross-validation with those different numbers, whichever one gets the best result. And another reason you want to use principal component regression is if there exists a lot of multicollinearity in your data. So we learned that principal component analysis works by finding linear combinations in your data. So if there's a lot of multicollinearity, which is just linear correlations, then ultimately when you use principal component analysis, you're going to be able to jam-pack a lot of that information or variance in the first few principal components. So ultimately, if there exists a lot of multicollinearity, you'd be able to get a Scree plot that looks something like this. where a lot of the information is to say in the first three principal components. But if there exists no multicollinearity, or there's no correlation in your data, then ultimately your Scree Plot will not see much improvements as you increase from each principal component. So what are the cons of using principal component analysis? So the cons are, since each principal component is essentially now a combination of all the variables, or it can be all the variables, you're going to lose a lot of the interpretability. Because you can no longer say, with an increase of x1, we expect a certain increase in y. Because that individual predictor is going to be based off all the variables, just with small portions from all the variables. Another con is it's not a feature selection technique. So the reason for this again is that each principal component has all the variables jam-packed inside of them. So not a feature selection, it's a dimension reduction. And then finally, when we're choosing our principal components, we're using an unsupervised learning algorithm that has nothing to do based on y. So even if our first, say, 4 principal components explain 85% of the variance, but that our remaining 15%, it doesn't help explain the data, but it could be very important in explaining the dependent variable. So essentially, you're trying to use an unsupervised learning technique to explain a supervised technique. So you could choose variance, or you could leave out important information. So that wraps up this section. It was definitely a doozy. Hopefully it helped you more than it hurt you. And I'll see you next time. Thanks.